Welcome to my video on the TI-84 plus CE calculator. In this video, I'm going to be solving some right triangle problems. Before we get started on that, we want to look at a right triangle in this acronym here, the SOHCAHTOA. And so what we've got, if we've got a right triangle, there's our 90-degree angle, there's our angle of interest, theta. So that's going to be the hypotenuse, that's going to be the opposite, that's going to be the adjacent. So the sine opposite over hypotenuse, sine opposite hypotenuse. So it's the opposite over the hypotenuse, that's the ratio for the sine. The cosine is defined as the ratio of the adjacent over the hypotenuse, those lengths, adjacent over the hypotenuse. And the tan of theta is opposite over adjacent, so opposite over adjacent. So when we have a right angle problem, we're always trying to figure out what angle we're interested in. And so that's why we remember these, because they help us solve real world problems. So for example 1, we're going to look at a building shadow. And this is actually a very real problem because you can solve, you don't know the height of a building just by knowing its shadow, and then the angle, which you can measure from the ground. You can calculate the height of a building. So here's your basic building. We'll put some windows in there and maybe a door. Now it casts a shadow, and we can measure with a tape measure. The shadow is going to be 40 feet long, and we can measure with a protractor setup that the angle is going to be 35 degrees. So here's our sun up here, and then that casts a shadow. So what we want to know is, how high is this building? So that's the question mark. Now in this example here, we're going to know, let's look at what we do know, or what we don't know. We do know this would be the angle theta right there. So we do know the adjacent, and we're looking for the opposite. So that would be the tangent. So in this case, the tangent of the angle 35 degrees is equal to the opposite over the adjacent, which is 40. Now we take that over there to solve for h. So 40 times the tan of 35 degrees is equal to the height of the building. So let's turn our calculator on. Let's clear it. It is in degree mode. We're going to be working in degrees, so that's good. We don't need to change anything there. So let's take the tangent of the angle, which is 35, enter, 0.7, with some extra digits in there, times 40, enter. So we're going to get basically the height is equal to 28 feet. So that's the height of the building. So there's our answer. It's just like a one-story building. So we calculate the height of the building knowing our trigonometry. Now let's look at a second example. In this one, we have got like an antenna or a pole, something sticking up, but we want to support it. And this is going to be with a guy wire. And a guy wire is a wire that attaches to something, to the ground here. And what we know is this guy wire is 30 feet long, and we know the angle we need is 55 degrees to get a proper guy wire. So really, what is this length right here? How far do we need to go out? How much room do we need? We've got this pole we want to support. So you're an engineer trying to figure out how much room we're going to need. It's a real world problem. To put this pole up and support it with a guy wire, we need a 55-degree angle. We got about 30 feet is the length. So let's look at this one. What do we know here? If we're going to be looking for L, which is going to be the adjacent to this angle, so it's going to be the adjacent, it's going to be the cosine of the tangent, but we know the hypotenuse, so it brings us down to the cosine. So we know the cosine of 55 degrees. That's the adjacent, which is L, we don't know, it's our unknown, and the hypotenuse is 30 feet. So doing our math, so we get 30 times the cosine of 55 is equal to this length. Make sure our calculator's on, clear it. And we're going to do the cosine of 55, close parentheses, enter, 0.573 times 30, enter. So that's going to be 17.2 feet. So we know that we need to be able to at least go out 17 feet before we can put this guy wire in place. Let's look at a third example. So there's our answer for this one, 17.2 feet approximately. In this case, we're building a ramp. It's going to be a wheelchair ramp. And the American Disabilities Act requires a ratio of 1 to 12. So what we're trying to do is calculate this angle because it's got to be less than around 5 degrees. For this wheelchair ramp, here's going to be going into the building. Maybe it's just building this example up here, and then here's the doorway going in. So what we know about this ramp is it's 24 feet from here to here. And there's our angle theta. We're trying to determine that. And then we know that the ramp is 2 feet high going up to the door. So is that going to be an angle less than 5 degrees? That's what we're trying to figure out. So we know the opposite and we know the adjacent. So the tangent of theta is equal to the opposite is 2, the adjacent is 24. So now what we want to do is we'll take the tan inverse of both sides. So we get theta is going to be equal to the tan inverse 24, 2 divided by 24. Let's get into our calculator, clear it. Now this time we're going to do second, and there's the tan inverse, the little blue, the second function, and we're going to do 2 divided by 24, close the parent, enter. So that's going to give us approximately 4.76 degrees. So that is less than 5 degrees. I think it's actually slightly less than 5. So we are compliant. This ramp is something we can build, and it is compliant with the American Disabilities Act. So that's a good thing. That's a good example. All right, well, I hope you learned a little bit about using your TI-84 calculator, some real-world problems using right triangles. I want to thank you for watching.